Welcome to another video from Lockdown Electronics with me, Bill, and this time we've got a bonus edition to the series on oscillators. So thanks to Eric Hardy, who commented on I think it was part 2 of the video, that what was I going to look at vacuum tube oscillators, and the answer to that question at the time was no, I hadn't thought of it. Now I don't have the facility to breadboard vacuum tube circuits because of the high voltages that I'd need to provide to the anode to actually get the things to work, and I simply don't have power supplies that will do that. But it is nonetheless a very interesting point. So I can actually show you some valve oscillators, because having given it a little bit of thought, I realised that actually I have got a couple of oscillators. So that's what I'm going to do. So it's a little bit different to the normal oscillator videos, but hopefully you'll find it useful. Now I just need to clear a couple of things up. Firstly, if you think that valves are very much yesterday's technology, yeah, in one sense they are. When I was a lad, most television sets were all valve, and it wasn't very long before they became transistorized, and only the display was a valve. And of course now we've got flat screens, so they've gone. So maybe it's tempting to think, no more valves. Well, don't be telling guitar players that, because most guitar players very much like the sound of a valve amp. Companies like Marshall and Fender and High Watt and Laney still produce valve amplifiers in considerable quantities, so plenty of valves knocking about there. But even closer to home, if you've got a microwave oven, it's highly likely that in the microwave oven there'll be something along the lines of a cavity magnetron as the microwave source, and that is also based on a thermionic valve. So yeah, in one sense they've gone, but in another actually they haven't. And I also need to address the elephant in the room. That's because, you see, I'm British, and in Britain vacuum tubes are called valves, and asking me to change the habits of a lifetime will be a challenge. So the terms are synonymous, but of course the Brits like to call them valves. But then of course the British are delightfully inconsistent, because for as long as I can remember, we might talk about a valve television set, but we'd also talk about it having a CRT as the display, so that'll be a cathode ray tube then. So we did call them cathode ray tubes. In fact, it would sound odd calling it a cathode ray valve, although I suppose arguably that would be correct if you were British. So please don't get too hung up on the terminology. I can't help what I just learnt as a kid. They're valves, they're tubes, it's the same sort of thing, but hopefully it'll make some sense anyway. So let's have a look at what I've got and how I might be able to show you a little bit of valve or vacuum tube oscillation. Now I said that I didn't have the facilities to breadboard valve circuits on the bench, which is quite correct. I do, however, have this British made Cosa 524 Melody Maker radio, which I refurbished 3 or 4 years ago, and it is indeed a valve set, and because it covers both AM and FM, it's from 1955, and so FM had just got going then, and it does cover 88 to 100 megahertz, because that's all the FM band was back then, as well as the long, medium and short waves. So that means this radio has 2 oscillators in it. So what I propose to do is we'll get the chassis out of the radio, and we'll see if we can get some instruments hooked up to the oscillators and see how they perform. Now before we do that, it's probably worth just having a quick recap on valves and how they work, and then having a look at the circuit diagram of this particular radio. So if you're a valve expert, you won't need to watch the next bit, because this is a very elementary explanation of valve operation by somebody who is most certainly not a valve expert. Okay, so valves quite often have a symbol something like that. This is a triode. I've picked the triode because actually both oscillators in the radio actually have triodes producing the oscillations. but it is possible to have valves with more elements than this. And real life triode looks a bit like that. This is a 1930s triode, a 6J5G, and this was in a signal generator I refurbished. Some very nice knot work on that string to hold the valve in place. So I'm pleased to say that valve was working perfectly and didn't need those rather nice knots undoing, and that means I didn't have to make a mess of remaking them. So what we've got then is at the bottom of the valve we've got a heater which does exactly what it says on the tin. It warms up the cathode and it encourages the cathode to emit electrons. A bit further up the valve we've got the grid. I'm going to come back to the grid in a moment or two, and at the top we've got the anode, and it's normal for an anode to have a positive charge on it, usually referred to as the B+, or sometimes HT, as in high tension. So first of at least 2 warnings you're going to get in these videos. Be careful, we are talking some serious faults here. In the radio we're going to look at, it's certainly so well over 270 volts on some of the anodes in that set, which is certainly quite a lot of volts. So the effect of heating the cathode, and if you do get the chance to look at some valves working, you can actually sometimes see that the heat is glowing away in the valve, causes the cathode to emit electrons, and they are attracted to the strong positive charge on the anode. And if you've just got a cathode and an anode, you've effectively there got a diode, because electrons will flow from cathode to anode, but they won't go back the other way. And indeed, again, this radio, although I'm not going to look at it, does have valve rectification. It's actually full wave valve rectification, but the principle is the same. In a triode we've got another element, which is the grid, and that grid literally is a mesh construction which doesn't particularly impede the flow of the electrons from cathode to anode. But what we can do is, depending on what voltage we apply to the grid, we can affect just how easy it is for those electrons to make that journey to the anode. So putting on a strong positive charge on the grid would reduce the flow to the anode. Putting on a negative charge would allow it to be enhanced, if you like. This is Bill here from the future. What I've just said there is incorrect, and I unintentionally misled you, for which I apologise. Thank you very much to those that have pointed that error out. Not being an expert in valves has caught me out. So it's very important that the grid is always negative with respect to the anode, because if not, that can damage the valve. So we don't want any of this positive stuff going on with the grid. Hope that clears things up. Apologies for the error. Now back to the video. And so what we're saying there is that a small change on the grid will result in a large change at the anode. In other words, amplification. And if that sounds a bit like a transistor or an FET, then it does. There's a lot of similarities here with a junction field effect transistor. The principle is very similar. So let's go on to oscillation, which was the whole point of this. So here's a circuit taken from the Radio Amateurs Handbook, 2nd edition, 1949. Actually, I think it's probably a little bit before 1949. Certainly the edition I've got is a wartime one. I was lucky enough to pick it up in a second-hand bookshop. But here's a circuit of an oscillator, and if you're wanting to actually have a look at this this book, it's got quite a lot of information about valves, and it's got lots and lots of stuff about valve oscillators in the chapter on transmitters. You can actually do that, because the very nice people at World Radio History have actually put it, they've scanned it, and it's up there on their website. So I will include in the description a link to World Radio History website, which is excellent. Encourage you to support that, and also a direct link to the download of the PDF for this particular book, and you can find it on, as it says in there, on page 87 in that book, if you want to see where it all comes from. But essentially what we've got here is we've got a triode. This one has got a directly heated cathode, but it doesn't really matter for the purpose of the explanation. And you can see we've got amplification going on, and the L1 is magnetically coupled to L2, which allows feedback to occur, and it's also possible for feedback to occur through C4 back towards the cathode. And finally the RFC, it's not a common phrase these days, that's radio frequency coil. That's done to stop the oscillations getting back onto the supply rail. So there's an example of a straightforward, fairly simple example of a valve oscillator. Okay, before we look at the radio, let's just look at the circuit. Now it's here's the circuit diagram, and again many thanks to radiomuseum.org for having such a fine repository of circuit diagrams. This one is got from there, and I recommend you have a look at their website too. But this is a fascinating radio because on the left hand side we've got the VHF front end, an oscillator, which consists of valve 1, marked there up as valve 1A and valve 1B. Valve 1B is the oscillator, valve 1A is the RF amplifier. Next chunk of circuit here is the medium and high frequency front end with its ferrite rod antenna, and we've got another double valve there, V2. We've got a triode V2A, who's the oscillator, and V2B is actually a pentode, I think, which is the mixer and RF amplifier. Then we've got an IF, and this is a fascinating bit of kit because we've actually got an IF that deals with both 470 kilohertz for the AM and 10.7 megahertz for the VHF FM, and you can see there's double sets of IF transformers there. And valve 3, which is the main IF amplification stage, amplifies both has sufficient bandwidth to amplify 470 and 10.7 megahertz. And then on the right we've got detectors and audio amp. The little bit of circuitry at the bottom I mentioned before, that's the full wave valve rectifier that provides the power for the radio. So it's a fascinating circuit, and we're only really going to look at the front ends. So let's have a quick close look at the front ends. So left hand side of that there we've got the VHF front end. Valve 1B is the oscillator. I'll mark it up there for you, and then to the right we've got valve 2A, which is the oscillator for the 470 kilohertz oscillator for the IF, sorry. So yeah, so what we're now going to do is we'll go and have a look at the radio, go and have a look where those two oscillators are located. We'll start with the one on the right, and you'll see that the VHF bit was very much an add-on, I think, in terms of this radio. So let's get off to the bench and have a look how all this works. Okay, here we are then with the radio set up on the bench, and first thing I'm going to try and look at is the low frequency oscillator for the medium, long and short wave. But just before I do that, if you just pay attention, I've got this meter set to DC volts, so I'm just going to pick up an earth somewhere just on the chassis there. I'm sure that'll do, and just want to go onto the connection on that diode, just around that capacitor. I don't know why I called it a diode. Okay, hopefully you can see that reasonably clearly. The display goes red. It's reading 286 volts, so that's considerably more than the main. So this is the B plus, as I mentioned before, the high tension, and you can see it's available there. That's driving the final anode of the output valve, and then there's another capacitor here, and that's slightly lower at 235 volts, both DC, and this is a dual capacitor with a common ground. So I wanted to just show you that because this is what you are dealing with if you're going to work with valve equipment. That's more than enough there to give you a considerable jolt, probably very serious. So yeah, 285.2 volts according to that, just sitting there. That's the one of the B pluses taken off the secondary, high tension secondary, and rectified. So there's plenty of voltage here, be careful. Okay, we'll take that meter out the way so we can concentrate on the reason for being here, which is to look at the oscillation. So I've got a scope probe here. Here's the display from the scope, you can see, and I've just got the probe attached to this long insulated probe with a clip on here, so I can poke about in here without having to touch anything that might cause me some grief, as I'm sure you can understand. So first place we're going to go, I'll show you on the circuit diagram here. We've got that valve 2, which is the AM long, medium and short wave oscillator and mixer, and V2, the right hand part of that valve. What I'm going to do now is connect to the grid of that, which is here. I'm just going to carefully try and grab the grid connection there, like so, and straight away you can see we've got a stable sine wave. So we're on long wave here. If I go to medium wave like that, we get a higher frequency, and you certainly saw the waveform change, and then short wave, higher again. So I'll go back to medium wave for now, and if I just tune up and down, you can see the frequency change in there. It's a lovely sine wave from this oscillator, this triode. It really does do a super job. You can see the amplitude changing slightly as we move up through the frequency range, and there is a noticeable change in amplitude. If I just alter the time base a little now, still we have got a really nice sine wave there at about 1.62 megahertz at the moment. And then if I go on to short wave, we obviously get a much higher frequency. Oscillator has now moved to 15.2 megahertz there. So if I just tune back down, we'll come back down here. That's around 10 megahertz as we come back down the shortwave band. So yeah, you can see the oscillator's working very, very well indeed. Now if I go back to the medium wave and correct the time base so we can actually see something, and I'm going to just put a little bit of volume on, and I'm just going to tune a station in, if I can find it. Make sure I really am on that's long wave, medium. Yeah, I am. So we've got some speech there. So what I'm going to do now is just going to move up to the next valve along, which is V3. I'm going to go to the grid of V3 if I can get to it, which I think is about here. Perhaps not. Perhaps it's there. No, perhaps I'm in the wrong place. Ah yeah, I'm in the wrong place, apologies. Right, here's the grid of V3. So that's the output of the IF. So if I turn up the gain a little bit, you can see there we have got the audio coming through, and if I adjust the time base to something that's a bit more considerably slower, we do indeed have, if I now just pause that, we should get no, I'm not, well, I've got too much noise on there. Let's see if I can get a better station. There we go. So if I pause that now, right, not quite so easy with speech, but you can hopefully see the envelope changing. I'm going to try and catch that. Yeah, there we go. Just turn that down. I'm sure you don't want to listen to MPs. So that's your classic AM modulation envelope, and that's just entering that that V3, which is the last stage of IF amplification. After that it goes to a detector. So yeah, that's the oscillator and its attendant mixed frequency that you can see. So hopefully that's made some sense. Okay, here we are with the radio now turned around. On this radio, the FM receiver is actually in this box here, which is completely shielded. You have to actually remove the cover to do any work inside it, and it definitely looks, and probably is, a bolt-on to some kind of original chassis or design. This is the sort of the FM bit, and we've got a takeoff from the AM tuning capacitor, which is behind this little panel here, and we've got these two cords which come up, and we've got two inductors here, and when you turn the tuner, those two inductors, the cores move in and out. They're on a spring at that end, and that is how the FM part is tuned in gang with the rest of the radio. So it's a variable inductor, two variable inductors, rather than a variable capacitor. So it's very elaborate. It's unimaginable they would build anything like this today. So the double triode valve V1, I'll just show it you here now. So the right hand side of that valve on the circuit diagram shown as V1B is the triode that does the oscillating. The valve is just behind here. It's a 6AQ8. It's just behind here, and there's the valve base. And if you're wondering what on earth this is here, I've got a little clip clipped on there. I've got 100 nanofarad capacitor here, a very high voltage one, and that's because I've actually got that clipped to the anode, which will have some high tension on it, and I've no desire to introduce that kind of DC voltage into my oscilloscope. It probably should handle it, but there's no harm in taking precautions. So I'm just going to connect the scope probe now to the other side of that capacitor. Now, I've had a few problems getting a decent connection, so I apologise for that, but there is the oscillation. I'm sorry about that. There we go, that'll settle down a bit for you. And yeah, that's about 9.52 megahertz. So if I now turn the tuner, I doubt you can see this on the camera, but those two slugs are moving up and down the inductor, and we're in opposite directions, and you can see the oscillator changing frequency. So if I just move up and back down again, we're at about 9.5 megahertz there. But again, as you can see, if I just alter the time base slightly, we have got a very good sine wave coming off that that oscillator. So there's a couple of examples of oscillators using valves, or as some of you like to call them, vacuum tubes, and they're about the best I can do. I don't want to be trotting around on the bench generating the kind of voltages that these anodes want. But yeah, might be old technology, but it's capable of producing some very nice and very accurate looking sine waves, as indeed it's had lots of years to perfect this kind of thing. So there you go, that's VHF oscillator. Okay, well there you have valves oscillating. Appreciate it's been a bit of a different sort of oscillator series video, but hopefully it's been interesting and some use. So thanks very much for watching. Please don't forget to click like and click subscribe if you haven't already. That really helps the channel, and I look forward to seeing you on the next video.